Hi, my name is Bartosz Miluski and I'm a blogger from Seattle. Welcome to my category theory talk. Let's start with the definition of product. No, just kidding. Okay, maybe 2 years from now, okay, judging by the pace at which functional programming is taking over the world, that might happen soon. Today I want to talk about functional data structures in C++. Now, I am really happy to see that there is much more talk about functional programming at C++ conferences. And I think everybody here, well, who haven't heard of Haskell? Okay, so like a few years ago, that would be everybody. Well, maybe not everybody, but most people. And a few years ago, the word monad was considered like bad language. They would beep me probably when I spoke about monads. And in this conference, the word monad even was in the titles of some of the talks. So making progress. So what is it about functional programming? Why is it something? It's a new hobby, or is it something that we have to pay attention to? And I think we have to pay very, very close attention to functional programming because times are changing. So there are paradigm shifts, and they usually happen in response to external stimuli. The environment changes. Something new happens that changes things in the environment. And we have to either adapt or die. In this case, the big change is Moore's law is finally over. Remember Moore's law? It's like every year, every 18 months, the speed of processors doubled. So you wrote your code and it was slow, but before it shipped, it was fast. Right? This is no longer true. If you write single-threaded code, it will be as slow, well, maybe a little bit faster in a year or two than it is right now, but not much. And there's been this cry to battle by Herb Satter, free lunch is over. That was many years ago, right? So what happened is we kind of slowly started thinking about it, but not really fast. And I think what helped us is that the new devices appeared, the portable devices, and they were still mostly single-core devices. So there was like a new area in which we could start programming stuff and still forget about multi-core. But even this is changing. So I don't know how many people here have 2 cores in their phone. Okay, right. Is there anybody with 4 cores? Wow. Okay. So 8 cores, anybody? No kidding. Aha. All right. So if the pace continues, we will all have to learn to write concurrent programs, and not just write a concurrent program that it takes us a year to debug. We'll have to have turnover. Okay, we'll have to be able to quickly write these concurrent programs on parallel programs. We'll have to use these other cores. So there is a paradigm shift. And what are these paradigms in programming? I mean, for many, many years, I've been a great I loved object-oriented programming. Okay? Object-oriented paradigm is great. And what is it about the object-oriented paradigm that I loved so much? Is that it's composable. And I think The most important thing, if this is one thing that you should remember from my talk, is composability is the most important thing in programming. Because this is how we humans work, not computers. Computers don't care about composability. We do. Because when we solve a problem, the only way we know how to solve a complex problem is to split it into smaller problems. Then solve each small problem separately, and then compose the solutions. And in this step of composing the solutions, this is what we do in our programs. We compose bigger programs from smaller things, be it objects or functions. And object-oriented programming provided us with this great opportunity to split things into objects, hide stuff inside an object. So the great thing about an object is that it has the inside and the outside and the surface. So when you are designing an object, when you are working on it, you are inside an object, and it's complex. But it's less complex than the whole world. But then when you are done with implementing the insides of your objects, then everybody else just sees the surface of your object. And the surface of the object is much, much smaller, much less complexity. And then we can go and take a bunch of these objects, which each of them has less complexity than their insides, and we can start composing them. Maybe inside a bigger object, and so on. So these are the things that are right about object-oriented programming. What's wrong with object-oriented programming? Objects don't compose with concurrency because objects hide the wrong kind of things. They're great at hiding stuff, not exposing them to the outside, but in a concurrent world, it turns out that they are hiding the wrong things. They hide data in a way that it's combined with both mutation and sharing. You have pointers inside objects, you have pointers between objects, and you have mutation. And that's a recipe for a data race. A data race is defined as one or more threads accessing the same memory, sharing, right? Sharing memory, and at least one of them mutating it. If nobody's mutating memory, then anybody can share it. But this mutation and sharing together, and when it's hidden inside an object, then you cannot compose anything without knowing exactly what's sitting in this object. What is this object doing to the data that I'm passing it? What is this object doing to other objects with which it's sharing data? What if these other objects are accessed by other threads? So, but there are some object-oriented languages that use concurrency, like Java, right? In Java, every object has its own lock. So maybe locking is good. No, locking is not the answer. It can solve a few problems, but the major problem with locks, and everybody who worked with locks knows that, they do not compose, right? There is this classic example. You have two bank accounts with locks. You withdraw, you take a lock, you withdraw money, you release the lock, right? But if you are moving money from one account to another, then what do? You lock this account, take the money. Do you release the lock and then take the lock to the other account? Well, but in the meanwhile, there's no money in your account, right? And then suddenly your mortgage company says, we are repossessing your home, right? So you hold on to this lock and you are trying to take the other lock, right, to finish the transfer. And in the meanwhile, your wife is accessing your bank account. And she's transferring the other way. She took a lock on this one, right? And now you're both deadlocked. So locks don't compose. If you want to implement transfer between accounts, you either have to expose these locks to the outside, right? Or create another lock on top which says everybody who comes to do anything with any of the account has to go through this lock. And of course then the performance goes downhill. So there are certain answers that functional languages, functional programmers have figured out. And they have figured out these things long time ago. And a lot of people say, okay, Haskell has been around for so long, and hasn't caught up. Why? And I think because there was no killer app for Haskell. The killer app for Haskell is concurrency. The killer app for functional programming is concurrency. So either we all switch to Haskell or we start thinking functionally in C++ and we try to evolve the language to be more functional, to allow us this kind of safer programming that's possible using functional methods. So immutability is one of these things that functional programmers have recognized as very important. You have data structures and you never modify them. And of course, if you don't modify your data structures, then you don't have any problems with concurrency, right? So immutability composes with data hiding. You can hide your data inside whatever function, closure, right? And you don't worry that there will be any leakage because it's immutable. It composes with data sharing because you don't care whether data is shared or not if it's immutable. You don't have to go around and copying your data because it changes. You can just have a bunch of pointers pointing at the same memory location if it never changes, right? It requires no synchronization because there is no possibility of data erase if you don't have mutation. Doesn't introduce long distance coupling. One object modifying something through a pointer and suddenly another object in another thread saying, what happened? Right? And now, of course, you would say, okay, but how can I program without mutation? Okay? Programming is all about changing stuff, right? Changing data. If I never change my data, then my program is dead. Okay? So the truth is that functional paradigm allows mutation, but in a very, very controlled way, so that it looks like there is no mutation. All mutation is done behind the scenes, at the bottom. It's the runtime that's doing the mutation for you and making it in such a way that it's totally safe, right? So mutation is not exposed. There is mutation. And if we want to implement functional data structures in C++, we will have to do plenty of mutation. But this mutation will be controlled. So what are these persistent data structures? They are called persistent, and don't confuse this with data structures that you can serialize to disk, right? These are data structures used in functional languages, and they simply replace mutation with construction. So what is mutation? You give me an object, and I return you an object that has something tiny bit in it changed, right? There are two ways of doing this, destructive and non-destructive, right? I can destroy your object by making the mutation, or I can give you a new object that's identical to your object with this little change. Is this mutation or not? I don't know. It depends how you look at it. You have a different object now. It's mutated, but you haven't touched the other object, right? So you have like the best of both worlds. So these persistent data structures, they embody the composition of immutability, right? So if you have just immutability, you don't know what to do with this. But if you have persistent data structures that allow this kind of controlled mutation, then you can compose immutability to create more complex system in which everything is immutable and yet they mutate. And in order to make this efficient, there has to be a lot of sharing. Because of course you can say, okay, I can mutate a vector, right? I can change one element in a vector. How can I do this without mutation? I would have to copy the whole vector and make the change, right? Now that's very inefficient. So if you are dealing with vectors, I don't think this is a good paradigm for dealing with vectors. So you have to have data structures that allow large amounts of sharing. But then again, since we are talking about immutable objects, sharing is okay, right? So rather than copying data around, you just keep sharing and you just keep resharing and changing the way you are sharing things. I'll show you examples and you'll see exactly how it works. Now, the bonus is that since you are not modifying anything, all the versions of objects persist. That's why they are called persistent data structures. They persist. They don't disappear. I mean, you can get rid of them if you want to, but they don't by themselves. When you mutate something, the old version is gone, right? If you want to restore the old version, you have to unmutate it, which is a complex operation. So this fact that you don't have, that they persist, that's actually very useful. Okay, so just to repeat, thread safety. No data race without mutation. So you don't have to worry. You can write your concurrent programs very easily, and I will show you an example in which I take a program, make it concurrent, and I don't worry about data races. There is one part of the program in which mutation happens. And that's when you are creating new objects, right? I said, you give me an old object, and I'll give you a new object with a mutation. During this process, I'm creating a new object, and I'm mutating it. So this part is called the construction, right? And during constructions, there is mutation. But there is mutation only of the object that you are constructing. And during construction, there is only one thread that has access to this object. So this is perfectly safe, okay? What is not usually appreciated is that if you are doing construction of objects in a multi-threaded environment, and then you pass it to another thread, or another thread gets access to it, you have to worry about so-called publication safety. It means you think you are done constructing your object, right? You finished, but the changes that you made during construction of the object to memory, they have not propagated yet to other cores, right? There are caches. There is, okay? So the solution to this is, well, there are two cases. In one case, you created an object, and then you create a thread and give it access to this object, right? In that case, there's nothing to worry, because the moment of creation of a thread is a synchronization point, right? And that's safe. That kind of flushes the cache, and everybody can see the object that you have just finished, right? The other case is when you create a new object, but a thread is already running the other thread, right? And you pass this object to this other thread, okay? Then the synchronization is usually done through the channel through which you are passing. There's always some way of passing data from thread to thread, and this channel is always responsible for making this safe, putting a barrier at that point, okay? So I'm just saying that so that you know that even though you are dealing with immutable objects, there are some concerns about synchronization, but they are taken care of. Now, in functional languages, you don't have to worry about resource management or memory management, right? In this case, I mean, resource management is a problem everywhere. That's independent. Memory management, I should have said memory management. Because you have garbage collection. In C++, we don't have garbage collection. So the problem is, if you have these immutable data structures that do a lot of sharing behind the scenes, who's responsible for releasing this data, right? This is no longer attached to a particular scope, right? So you cannot do the usual constructor-destructor pairing, right? So you have to use some other way. And the other way, there are just two ways of managing memory. One is garbage collection, the other is reference counting, right? And there's a spectrum in between these two. So we have to do reference counting, and fortunately we have these wonderful objects called shared pointers. They do reference counting for us, and they do it in a thread-safe way, and they are optimized. They are optimized to not use locks. They do this using lock-free algorithms and so on. Hopefully every compiler has a very good implementation for a particular architecture of the processor that's lock-free and reasonably fast. And just a little aside, you always use make shared when you are dealing with shared pointers if you can, because that increases the collocation of data, right? So your object that you are probably going to access anyway, right, sits in the same cache line as your reference count. That's kind of important. So here's the first example. I haven't really implemented this, but this is something that probably Sean Parent would appreciate. How to implement a document using persistent data structures. So let me show you. So imagine that a document is a tree structure, right? It has a root and there's chapters. Within chapters you have paragraphs. Within paragraphs you have these spans that have different formatting and so on, maybe even down to single characters, right? So it's a tree. So if you can implement this document as a persistent tree, meaning you never modify it, it's every time you make an edit, you create a new version with this tiny change, right? And you just do your pointer magic so that you have pointers to previous parts of the document that haven't changed, so that it's reasonably cheap to keep all these versions around that don't take any additional space except for the few pointers, right? Then suddenly so many things become trivial, like undo, right? Undo means just go back to this previous version that you have right here, right? You don't have to store all the commands in a queue and then go and for every command implement undo that has to be perfect, right? I mean, how many times people implemented undo that actually is not a complete reverse of do, right? You can copy and paste parts of the document from old version to new version easily. Again, without any mutation. But you have these old versions. And then you can do concurrent operations in the background. You can run your spell checker. You just tell the spell checker, go and spell check the current version. And if the user keeps typing, they are just creating new versions of the document. There's no mutation. The spell checker doesn't have to lock anything, right? There's no data race. Saving the document is trivial. Just save the current version and let the user continue. You don't have to copy the current version on the side and then put it in on disk, right? You just have this version here. You just serialize it to disk at your leisure. Second example, and this is an example in which I will actually show you code. It's a simple enough example, trivial enough, but it shows you some powerful features of persistent data structures. So this is the famous 8 queens problem, where you on a chessboard you have to position queens so that they don't attack each other. So for every row there has to be only one queen, for every column and every diagonal just one queen. So this is an example of a solution. Okay, we'll do it for an arbitrary size of the chessboard. So how do you approach this problem? Okay, this is actually a very simple problem, right? I mean, position the first queen, let's say at the top row. Well, you have all these possibilities. So just create a list of all these possibilities. One, the first column, second column, third column, fourth column. Okay. So these are your partial solutions. Then for each partial solution, add one queen to the second row. Okay? And every time you are adding the queen, check, oh, is it in conflict with the previous one, right? So like you can put it here, you can put it here, but you don't want to put it here, here, or here, because this one will be attacked by the other queen. Okay? So you get a list of partial solutions that are based on the previous solution. And you create this tree. Go down. You create all these possible solutions, except for the ones in which you pruned because they were obviously invalid, right? And then finally, if you get to the last row, you say, I'm done, record the solution, and continue with the next solution. So the description of this can be explained to, a preschooler. And this is called a divide and conquer kind of algorithm, right? So we have to have this object called partial solution, which has the first k rows filled with k queens, right? If k is equal dimension, let's say 8, then we are done. Otherwise, we refine the solution. So this is the refinement stage. Generate partial solutions, in this case with an unchecked queen in the k plus first row, right? And then recurse. Recursion, create the next. And this is a very generic divide and conquer pattern. This can be used to solve a tremendous number of different problems. Can we generalize it? Can we write an algorithm for that that's generic? Absolutely. Here's the generic algorithm. Is it possible to squeeze it a little? Somebody was able to do this. These are minus. No, I think you had to also press mute or no. This is dezoom. No, it was okay. Freeze image, time, input, menu. I think menu. You have to press menu, huh? No? Well, the designers of the UI on these things. Oh, yeah. Okay, that's good enough. That's good. Okay. So this is this function. Thank you. This is this function generate, and it's parameterized by two types. One type is called partial. That's the partial solution. And the other is the constraint. That's the constraint that I'll be checking, am I done yet or not? In our case, this will be just number of rows, dimension of the board, right? So what does generate do? Well, it checks, am I done? Am I finished? So partial solution must have this method is finished that takes the constraints. In our case, it will just very simply check whether there are 8 rows filled, right? And if we are done, then we get the solution out of this partial solution. So there has to be a method get solution. So we have a partial solution and just give me the solution, okay? So this, since this thing is supposed to return a standard vector of solutions, no, actually of final solutions, okay? So there is different type for solution and final solution. So partial : solution T is the type of the final solution. So it's a vector of final solutions. So I just create a single element vector of final solutions and I'm returning it, okay? But if I'm not done, then I call this method refine on my partial solution. I pass it the constraint. And this method refine returns a list of partial solutions that are refined. So they contain one more row. Okay? They contain one more queen in the next row. And then I go for each partial solution. So I go over all these partial solutions, right? And pass it. This is my own for each. So because I'm using my own list. So here's where the magic comes. This list is actually a persistent list. So for each is a for each for a persistent list. So I take this list of partial solutions, and this is the lambda that I'm going to apply to each partial solution. And what do I do with this partial solution, the new partial solution? I call generate again. Okay, so I'm calling myself recursively, but now I have a partial solution that's one queen more, right? And what does generate return? And returns the solution vector, the vector of final solutions, right? And all I have to do is concatenate this to accumulate, really. I should use some kind of accumulate algorithm, really. But I'm just doing it by hand. So I have this list of solutions. No, this one, solution vector, result. And I'm just copying it using the back inserter. So I'm appending my current vector of solutions to the existing vector of solution. And finally, I'm done. I'm returning it. Mm-hmm. No kidding. Oh, okay, cool. Thank you. I'll change that. Yes. Very good comment. Thank you. Okay, so this is pretty simple. It's pretty much a straightforward translation of what I said. I have sorry. Should repeat the comment. Okay, the comment from Sean was that I'm actually pessimizing the stuff by reserving, because I'm reserving just the amount I need, and I'm losing the doubling behavior if I was not reserving. That's a very good point. Okay, so let's continue the implementation. Now this is specific to the 8-queen problem. That one was a skeleton that can be applied to any problem that divide and conquer, right? Now I have to implement this class partial solution just for the 8-queen problem. Okay, so solution T, that's the final solution type. That's just a list of positions. Here I have the list of position, that's the queens. So this is like, you know, row column for each queen. So my final solution will be just a list of 8 positions. Okay, trivial thing. It has current row, so it starts from 0, you know, and says, in which row am I right now? Which row am I filling? There are 2 constructors. One constructor creates an empty solution to begin with, right, with current row 0. And then I have this is very characteristic for persistent data structures, because this is a persistent data structure, okay? When you create persistent data structures, you want to reuse as much material as possible from the previous one, right? So they always have this kind of constructor that takes a huge data structure. Well, in this case, it's not huge really, right? But potentially big data structure, and just stores a pointer to it, right? So I'm just copying this list, queens, over this list, queens, and this is nothing but just storing a pointer. I'll show you the implementation of persistent list, right? But it's one pointer operation, okay? Now I have to implement these 3 methods, right? Get solution, that's what I was using in the skeleton. Get solution just returns the list of queens, right? Is finished takes this constrained object, right? Constrained object in our case is just an integer dimension, and checks is current row equal dimension. So that's the number 8 for 8-queen problem. And then there's this refine that returns a list of partial solutions. And maybe I should mention, you should notice this const here, okay? This is very characteristic for functional programming, that you don't want to modify your data. Now, this contains just one integer and one persistent data structure. So this thing is persistent. And I'm never modifying, there's no method to modify current row, right? So it's persistent. This is all the interface. So here's the implementation of refine. So that's the method that takes, takes this. This is the current solution, partial solution. And I want to produce a list of next row partial solutions, right? So how do I do this? Well, I start with an empty list of partial solutions. And now I'm iterating over columns from 0 to dimension, right? Iterating over these columns and trying to add 1 queen to each column. And I have this private method, I don't know if you've seen this, is allowed. So it takes a position and compares it with the positions of all other queens and says, you know, am I under attack or not? So if it's allowed, if it's not under attack, then I create a new partial solution that corresponds to this queen being put in that position, right? So I'm creating it, so I'm using this constructor of partial solution, which takes current row plus 1, because I'm advanced my row, and I take the queens from my current solution, and I push front this new position. So that's the column that I'm at, and that's the current row that I'm filling, right? Now, I call it push front, and I don't know, maybe people will be protesting, because this is a non-destructive push, okay? It does not destroy the current queens list. It just gives me a new list, okay? But since this list is a persistent data structure, it only does a little bit of pointer magic, nothing more. It's just sharing this whole tail, okay? So now I have a new partial solution, and I'm saying push front on this partial list. Now here, I could have done it using recursion, and then you wouldn't see this. This is, I'm saying, I'm okay with mutation. Okay? I'm just overwriting the old list of partial solutions with the new list of partial solutions that was returned from push front. And again, this is a very cheap operation. It's just a pointer. What it does behind is actually, since this is a shared pointer, it decrements reference count on the previous one, but then increases increments. So I'm like this kung fu master, you know, street fighting, mixing functional programming with mutation, right? Yes?
So the point is that parts is local to this
Yes.
stack frame and therefore local to this thread.
Exactly. So the comment is parts is just local to this thread. It's only one thread that's accessing it. I can do whatever I want. I can do mutation. Nobody cares. So notice again, push front is a constant method. It does not really push stuff on the front. It just gives me a new list. Yes?
Call it cons.
Hmm?
Call it cons.
Call it cons? Cons, yeah. That's what I called it in the beginning, but I don't know. With this crowd, I'm not sure. What's a better name? Now notice what is that there's an interesting thing happening here, because normally when you would implement this algorithm, you would do backtracking, right? I'm sure that's how you would implement. And it would be much more complex. Because you would be going sort of vertically down the branch of solutions. And then when you get to the end, I mean, either you get to the very end and you have a solution, or you have to start again. Yeah, you have to backtrack. And at every backtracking step, you unmutate whatever you've mutated and so on, right? And here this is done with persistence instead of backtracking. These two ideas are kind of exchangeable. Not completely, and I'll talk a little bit more about this, but we have traded persistence versus backtracking, and it made this algorithm extremely simple. It's really simple. I mean, if you don't see the simplicity of this, then you should try implementing it with backtracking. Okay? Homework, assignment. Okay. Well, before I show you this, let's go back to generate, right? I want to make this parallel. Am I crazy? I mean, here's a loop, yeah, right? It's a for each loop. Why don't I do this in parallel? I can just create a bunch of threads, right? Each of them would call generate. And I would just combine the results. And I'll be done, huh? This is how you are supposed to do parallelization, okay? And anybody who did concurrent programming in their lives must recognize that I'm doing something really crazy and dangerous, right? This is a bomb and I'm diffusing it, okay? Which wire should I cut, the blue one or the red one? But I used persistent data structures. I can do it like this, and I'm not afraid. So one thing to remember is that if I make it completely parallel and I go all the way down and create threads for every single level, I will generate too many threads, right? Because I would generate threads for every single branch down to the leaves of all possible solutions, which is like, I don't know, 8 to the power of 8 or whatever, right? So in all this kind of parallel solutions, you want to stop parallelizing at some, you want to throttle it, right? So I will add one more argument to generate, which will just give me the depth to which I want to go parallel. And when I get to this depth, I will just switch back to this solution, which is sequential, right? So there's a slight, one more parameter. And let's see how this is implemented. Generate par. So the first argument, integer depth. I'll be decrementing it until it hits 0. So when it hits 0, then I switch to generate. That was the sequential solution. Cool. Otherwise, I ask, is finished? Okay, well then return the solution, right? Nothing changed. Otherwise, okay, now I have to think a little bit. I have to create a vector of futures, right? Because I'm now spreading my work among threads. So I need a list of futures, and then I go over this loop. So I'm doing it really by hand. I mean, this probably could be some higher order parallel loops implemented and so on. But I want to show you all the details. So inside this loop, for each partial solution, I will start async. I will start a new thread, right? I will capture these things into my lambda. And inside this lambda, I will call generate par recursively, right? So this is identical to the previous thing. And async returns a future of solution vector. So this is the final solutions. And I'll push back this future on my vector of futures, right? So I'll end up with a huge vector of futures. And at the end, I will call when all. This is not part of the standard yet, but this is this barrier where we are waiting for all these futures to finish. When they are all finished, they will give you a vector of solutions, and then you want to concatenate all these solutions together. So I have a function concat all that concatenates a bunch of vectors, right? And that's it. I have parallelized the stuff. Okay? So notice I parallelized the skeleton. I can reuse the skeleton with any divide and conquer algorithm, right? And as long as my data types, my partial, especially my partial, is a persistent data structure, this will work. That's the only condition. Partial has to be a persistent data structure. And this will work. So now you, of course, want to see the implementation, right? Persistent list. And I'm glad that David has this talk about algebraic data structures, because this is, I was afraid to talk about algebraic data structures, and I'm not going to do that, but you will immediately recognize what I'm doing. Because I'm defining a list as an algebraic data structure. I say a list is either empty, right? Either or is a tuple element, which is the head of the list, and another list, which is the tail of the list, right? And these kind of definitions, these kind of algebraic definitions, that they very nicely translate into constructors of my data structure. Because that just tells me that there are two constructors, empty and this one. So list of nothing, that's the empty constructor, and the other one will take an element and a list. So the other one takes element of type T and a list, that's the tail. Okay? Now how do I implement it internally? Well, it's an either or thingy. So probably the simplest implementation, I mean, I could implement this with a Boolean and so on, make it complicated. But in this case, the simplest implementation is just a pointer. Pointer can be a null pointer or non-null pointer. If it's null pointer, that's an empty list. If it's non-null pointer, then it's a non-empty list, right? So I put a pointer. Where is it? Here. It's a pointer to a constant item. Okay? It's a persistent data structure. I will never mutate it. The item is const. And this item contains the value and contains a pointer to a const next item, and so on. So, I mean, you've seen the implementation of a linked list a million times, right? So this is just one of the variations of it. Right? And null pointer is the encoding of an empty list for us, right here. Okay? Now, of course, it says here, as if we had garbage collection, right? I can't have a destructor here because I'm sharing everything, okay? I'm sharing. This is a pointer. This is I got some list, and I just took the head out of this list. It's a pointer, and I stored it in here, right? So I'm taking a pointer out of this, putting it here, and now I'm sharing it, okay, with my donor. So of course I have to implement it. Oh, okay. Before I say that, let me implement the other methods, okay? So is empty obviously checks whether the pointer is null. Front asserts that it's not empty, takes the value from the head. And pop front and push front are both const method, and they both create a new list. So pop front will create a new list from the tail of this, right? And this is a constructor that's a private constructor that I haven't even listed, right? Because nobody else should be using it. That's not for the users. It's the internal thing. And push front creates a new list with this value and this as its tail. And again, it's just taking a pointer. It's all pointer manipulation. So here's the version that does not use garbage collection. Right? So instead of a pointer, it has a shared pointer to next. And notice the changes are very simple. It's almost mechanical. You know, you change this to a shared pointer inside item. You change the head to shared pointer. Okay, what else? Well, there's this change. As I said, make shared when you are allocating a new pointer you want to make shared. Right? Yes? Which part? By value. Okay, so the comment is pass this shared pointer by value and save yourself and move it into place. Thank you, Jean. Excellent. Excellent. Yes. Move semantics. I was just going back and forth between move semantics and reference semantics. I'm still not very well versed in it. That could really screw you up. Okay, so it's better to assert. It's better to assert because it's a precondition. Yeah. So the question was, would it be okay to just return an empty list if pop front is called on an empty list? And theoretically, yes, but it's against the definition of yes. this one, would it be okay to return a const ref? Yeah. As I said, I'm kind of tossed between these. Yes?
As far as assert versus return end list, if the precondition is the vertical confines, most automatically, once the pass are empty list, it's undefined matrix with vertical confines.
Yes. Yes. Yeah. So the comment is, if this assert, I mean, if the precondition is you can only call pop front on a non-empty list, then this would be undefined behavior and you can assert. And that's exactly what it is. It's undefined behavior. Okay. So now I want to develop this in a slightly different direction. And as I said, this solution is breadth first, right? I go 30 minutes? Okay. I go breadth first, right? I go every level, fill it with partial solutions, and for each of them I fill with partial solutions and so on. Whereas if you were doing a backtracking algorithm, you would go depth first, right? And arguably, depth first requires less storage, right? Even though we have these persistent data structures that share a lot of stuff, still there will be an explosion, okay? So is it really better? Is it better to do backtracking solution? And the thing is that you can turn this greedy breadth first solution into depth first solution by making just one small change. Make this list lazy so that you never evaluate the whole list of partial solutions that you got, right? Just evaluate one by one. Store them lazily, only when you need them, which has this great advantage that your algorithm still looks almost the same, but behaves completely differently. It just looks like you are getting a whole list of partial solutions, right? But you are really getting only one, and the promise for the rest of them. And then you continue with this first one, and then go one level deeper, and you get all partial solutions for this one. Yeah, but you're really getting just one, and the tail that's in the future, right? And so on, until you get to the very bottom of it, right? And you have just traversed the branch with const storage. Well, not logarithmic storage, right? And then you come back, and you hit the next element in one of these tails, right? And it's evaluated then. So this can be done very cleverly. So I'm going to rewrite this algorithm. Okay, so this is my new version of generate, where instead of using list, I use stream. That's my lazy list. I call it stream. Okay? So refine, instead of returning a list, returns this lazy list called stream. What's important here is that my for each, the one that I implemented, it's greedy for each. It consumes the stream. Because it could go through the stream, right, one by one, and of course it would evaluate the next value in the stream and so on and so on. But if it doesn't deallocate the ones that it's already gone, then I'm increasing my storage. I want const storage at every level. Okay? At every level of the tree, I want const storage. So this is for each, that if you move your partial list, and you have to move it so that there is no dangling reference to it, because if there is a dangling reference out there, then there will be +1 ref count on every element of the list, right? And you will never get rid of it. So I move the list and I greedily consume it. I have to change my partial solution now. And this is maybe, I could have started with a recursive solution, okay? I showed you a solution with a loop, iterative solution, because I know you're used to it, right? If I want to do this lazily, I really have to go into sort of a recursive kind of thinking. So recursive loop over all the columns in a row, okay? So I will say I'll start with some column, right? And I will call refine row for column no, this is dimension, sorry. Refine row for column 0 dim, and this will do the refining for 0 and recursively for 1, which will recurse into 2 and so on. So like in every recursive algorithm, you start by finding out if you are done. You're done. Well, here you start by greedily eliminating solutions. So you really can do it up front. Like you go through these rows and see if they are not allowed, then you can eliminate them right there on the spot. So that's the first thing. Is you're pruning. You find something that's possible. It's allowable. Okay. So if it's allowable, then let me see. Am I done? Well, so if I got to the end of the list, the column is equal dimension, I'm done. And I just return an empty stream. That's an empty stream, right? But if I found a viable solution, then I construct a lazy stream. And a lazy stream is constructed by passing it a function, a lambda. This is a lambda that will generate a cell in a stream. Okay? I'll show you the implementation of the stream in a moment. So it generates a cell that has a value and a tail. And the tail is also lazy stream. Okay? So the value that I want to put in my stream is this partial solution, just like previously, current row plus 1, queens, push front, new position, right? So that's my new solution, and that will be my partial solution, the head of my stream. The tail of my stream I get by recursively calling refine row with call plus 1. Okay? And finally, I'm creating a cell from value and stream. So that's my constructor for a cell. Okay? Now what happens is, even though it looks recursive, right? It looks recursive. I'm calling refine row here. It's not, right? Because this lambda is not evaluated here. This lambda is stored as a function pointer, as a function, right? And it will be called later, when it's needed. So later on, it will call refine row, but not right now. So you probably want to see the implementation of the lazy stream, right? And it's not the best implementation, I know, because Eric hasn't gotten to it yet. So he hasn't optimized it for me. But I'm sure when he gets at it, he will optimize the heck out of it, and it will be a totally acceptable thing. So again, algebraic data structures, and lazy stream can either be empty or it can be a suspended cell. So immediately two constructors, empty or suspended cell. Now suspended cell is created using a function. It's a function that returns a cell, right? This is the lambda that I was passing to the constructor there, right? So what I'm doing is I'm constructing the lazy cell, a shared pointer to a suspended cell with this function. So I'll show you what a suspended cell is, okay? So that's the stream, and it has a shared pointer of where I store a suspended cell. A suspended cell is just a function that I haven't executed yet, but it will produce the value that I want to put it there. So cell itself is very simple. A cell has a value and a lazy string, right? There's nothing interesting in it. Both these data structures are persistent. There is no mutation there. I can't mutate anything except for the hidden mutation. Like every time I say there's no mutation, right? You know that there is a hidden mutation. There is a shared pointer that has reference count in there, right? And here there's this suspended function that, of course, when I call it, eventually it will do execute something and store the value, right? So it's not really true. But from the perspective of the client, this is perfectly persistent data structure. Okay? So that's my cell. And now you want to know how the suspension works. So suspension is a memoized function. So it stores a function that I pass it. I pass it a function, right? And it stores it. So, and I store it as std function. And of course, everybody who knows anything about performance will shout at me, oh gosh, this std function is very slow. But I'm kind of lazy and I didn't want to go into this template hell. But it's possible to do, probably, I hope. We'll ask Eric. So it has this mutable t, the memoized value. So after I call the function, I will just memoize the value. So because this cell will be called many, many times. And I want it to be memoized. And it will be called from multiple threads, possibly, right? So since I want to make a thread safe, I implemented this as a call once thingy. So the first time you call get, call once is called with a special flag that's once flag that's defined by the standard. And I'm going to call this function set with a this pointer. And set will just call the function f that I stored and memoize the value that it returns. Yes?
So one little optimization you can do to free the memory that the function contains is that after you call the function the first time is to clear the function pointer or that function object, so then it won't hold on to the memory.
Uh-huh. So how can I? So the thing is that you can somehow clear the memory for this function. I'm not sure how do you clear it? Overwrite it with null? Okay. Yes? What? I guess maybe in this version it doesn't make sense. I think finally I made get const. Yeah, so there are some subtleties there that I just don't want to talk about, especially that there's not much time left. But I would love to discuss this. Yeah. Okay, so it's just a memoized function that with some synchronization. And this is the implementation of consuming for each. So it just, calls this get that I just showed you. So it forces the value. And then calls pop front, destructive pop front, so that it frees the previous value. Okay, so it keeps consuming the stuff. Now this disregard, it's I thought I had to implement value semantics, move semantics, but I think this is like automatically implemented for me as a default constructor, right? Am I sure? Is that true? Okay. So let's talk a little bit about performance. So this particular demo, this little program is just too toy-like to really measure performance. Nothing is happening there really, except for the stuff that matters. So I first implemented a different program. It was a conference timetable problem, which is also this kind of dynamic programming problem, very similar to this, but more complex. And it's more complex, and I had to use other persistent data structures like maps. I implemented red, black trees as persistent data structures, and I used them. So this is the book from which I took the this example. It's called Parallel and Concurrent Programming in Haskell by Simon Marlowe. Everybody should read this. Learn Haskell, read this to learn how to do parallel programming. It's really great. It's a great book. And I'm just going to go through this book and blog one example after another, translating into C++. Because it's really worth it. Okay? So the divide and conquer skeleton actually was from that problem. And I just took that skeleton and moved it to the 8-queen problem with almost no change. And I implemented parallel and lazy versions and all combinations. And I tested the performance. And of course, Haskell does not have the same performance as C++, right? So you'd probably expect, okay, 2-3 times slower. Huh? 3 orders of magnitude slower. Haskell beats C++ by 3 orders of magnitude. Okay? All right. So yes, this is my naive implementation of Haskell. Okay, I looked at how Haskell implements these things, and I simply translated them into C++. So I translated not only the program but also the implementations. I translated parts of the implementation of the Haskell runtime in a way, in a sense, right? And this is the kind of performance I got. And I'm take it with a grain of salt, absolutely, okay? And I'm sure when Eric is finished with this, it will be just a few orders of, no, it will be as fast as Haskell, okay? Yes.
You have reference counting in Haskell.
Garbage collection.
Haskell, that's very different.
Yeah, but isn't manual memory management faster than garbage collection?
Not if you never run out of space.
Yeah, that's true. That's true. Yeah, it should be tested with like without any deallocations. Yes.
With the approach you're taking of basically never deleting any of your data until you're done with the whole thing,
Yeah.
you could easily just do a area based where you use custom allocation
Mhm.
of some sort.
Yeah, I was thinking.
Don't delete anything.
Right. Okay. So
No shared reference.
So the suggestion is just never to delete anything and use some kind of custom allocator. And I thought about using a custom allocator with shared pointer, but it's no shared pointer whatsoever. Okay. Yeah. Yeah. Okay. So naive C++ implementation is bad. Okay. But I'm sure it can be improved. Yes?
Well, that's actually what kind of strikes me, because it seems that your intention was to implement the algorithm exactly as Haskell does.
Yes.
So I wouldn't. So where is the difference coming from? The algorithm is the same.
Yeah.
It almost begs the question: if we're using the same algorithm, it should be pretty much the same between languages, except for the issue of whether it's interpreted or whether it's.
It's not interpreted. No, Haskell is not
My
interpreted.
question is, your example really begs it cries out for an answer.
So let me repeat the question for the camera. I have to. Oh, okay. So the comment is that this just cries for an answer. because the question is, why is it so slow? What is it really? And I have some theories, but Sean has, yes.
So you're not using root, you don't enough on the shared pointer.
Okay, not enough move on shared pointers, yes. Mm-hmm. Huge overhead with std function, yes. Mm-hmm. Agreed. Huge overhead with this kind of synchronization that I'm using. Okay, the call once. Oh, horrible. Spinning up a thread on yes. I mean, Haskell is using lightweight tasks. I'm using very, very heavyweight threads, obviously. Yes. Yes. Okay, so Sean can send me half a page of code that that implements lightweight tasks. Excellent. That's what I was expecting to learn in this conference. Yes.
Did you try subjecting C++ code to a profiler to actually?
Did I try a profiler? Yes. And I saw that it was spending most of the time in NTDLL. Which is probably synchronization and probably memory allocation. No? What is it? The starting of threads. But doesn't it reuse these threads somehow at some point? No? Yeah. Okay. But, no, I have to say something, okay? Even the synchronous one, the implementation was slower than Haskell by orders of magnitude. So it's not only parallel implementation, it's my stupid synchronous implementation that was so bad. And maybe move semantics will help some, I don't know. And I think memory management is probably the biggest hit. The allocation, deallocation, allocation, deallocation, that's just killing it. Yes. Okay? Yes?
One downside that memory implementations then optimized for small memory allocation. So Nestle or Java or any virtualized language, you're doing a lot of memory allocation. So stack you're working with public private. That's why stacks are optimized for very large amounts of small memory allocation.
Mm-hmm.
Whereas C++ is the opposite.
Yes.
Allocate lots for objects, you're able to further small.
Okay, so the comment is that all these languages with garbage collection, and especially languages like Haskell, in which they are optimized for large numbers of tiny memory allocations. And it's absolutely true, yes. Whereas C++ allocator is good at allocating huge slabs of memory. Yes?
Modern concurrent garbage collection is just way better at managing the memory of many threads than parallel.
Yeah.
Reference counting, which keeps synchronizing between the threads
Mm-hmm.
and then locking the entire heap just to free that one object, and that's the next. You may have many threads. It would be interesting to see how many of them actually run in parallel.
Uh-huh.
And in the non-threaded version, you all have all these overheads anyway.
Yes.
Still have
Well, if your allocation locks the entire thread, the entire heap of the entire program, then your allocator is back.
Yeah, so the comment is all about allocators. That if you lock the whole allocator every time you allocate, then that's really disastrous. Yes, and I was using, by the way, the compiler that was Microsoft Visual Studio 2013.
Probably hard to figure out if you have any idea how many of those things were allocated and destroyed on the same thread, how many were moving across threads.
Yeah, that's a good point. It would be interesting to see how many of these objects were moved across threads and how many were just used. I'm afraid they are accessed by many threads. Yeah. Right. So it's created in one thread and deleted in another. It's very likely. I mean, all this code is on GitHub. Okay, I put all this code on GitHub. So please go ahead and try to figure out why it's so slow, and some of these problems probably are because I'm not such a great programmer, and they can be fixed, and I'm not using the C++ 11 very well, and so on. So maybe one order of magnitude can be shaved off by this, but if I'm afraid it might be pointing at some problems that are just there, that mean that C++ is still not ready for the parallel age. Okay? And one of these examples is memory allocation. That we are so happy with the memory allocator in C++, but it's always used in the same way to allocate these slabs of memory, the vectors. And here, when you are using fine-grained algorithms and multi-threaded algorithms, that might really be bad. 5 minutes. Okay. More questions? Okay. So I won't have time for it. I could talk for another hour easily. Okay. So let me just summarize this. You know, there are tremendous advantages of this. If we can figure out the performance, then this would be a wonderful way of implementing things, because this is so easy to write programs, right? Implementation follows the algorithm, and it's not following the complex algorithm. It's following the brute force algorithm, right? And it implements it relatively efficiently, because instead of doing the backtracking, it's actually sharing a lot of data structures and so on. It's very composable. These persistent data structures, they compose beautifully. I mean, you've seen just tiny bit of composition, right? I mean, you had a list, you had a stream, now you had these partial solutions, right? But you can build very complex persistent data structures for smaller persistent data structures. And it's not a problem. And there's this orthogonality of concerns that you can switch between sequential and parallel very easily without worrying about the stuff exploding, right? This is like the first example where I could actually take a serial algorithm and parallelize it, and it runs the first time. Really. After it compiled, it ran correctly the first time. And then you can switch between eager and lazy evaluation so quickly, right? A few changes. I showed you where the changes were. They were very simple. If you had a library of streams of persistent data structures, you would be just like juggling these things and saying, well, let's see, maybe if I change this or if I change this, maybe it will run faster. Because parallel programming is all about experimenting. You never get speed up on the first try, right? You have to experiment, you have to profile, you have to see how deep you want to go. I mean, I have this depth parameter, right? And it makes things faster up to a certain level, at least in Haskell, right? And then slows it down. So yes. And you can combine, you can do sequential lazy or sequential eager or eager parallel and so on. So you have orthogonal issues that you can mix and match. So this is the kind of programming that really is fun, you know, and productive. Okay? Thank you.